We have a question in the Q&A here for Dr. Morawska about the saline administration to the airway, and what was how did this impact aerosol generation, not just with breathing, but with speaking and singing as well?
Looks like you're muted.
Lydia, you're muted. You want to go ahead and unmute yourself?
I opened my camera, I didn't realize. In this study, we didn't go into this analysis exactly what's happening during different activities like singing and so on, but we definitely noticed that whichever activities and whoever was speaking, it was affected by this airway hygiene. So by all means, there's much more studies needed, and in fact, we started more studies, but clearly this is a very important factor.
It seems like that topic sort of converges with some of the things that Lydia Bourouiba was talking about, and rheologic properties of the airways. Where is that saline, the salt solution being deposited? Is it just in upper airways, or is that getting out to the smaller airways where the bubble bursting in the airway closure reopening is happening?
I don't think I have an answer to this question because we didn't model this. It is applied to the upper, to the nose. So to what extent airflow will take some of them deeper, it probably will. But it is just qualitatively thinking about this. We have no quantification of this effect. I don't know, Lydia, did you do anything of this kind of analysis?
Not on injecting saline into subjects, but we did try to take samples initially from the bedside, and for at least mucus secretions, and clearly with the addition of saline was essentially really changing completely the rheology, making it. Of course, it's well known that that's a way to get the mucus out. So it decreases the viscosity, but interestingly, it increases slightly the surface tension. And so there's slight competing differences on how then it changed the fragmentation. But I think that was really a lot of saline in the respiratory tract, not just a local.
Just applying a little bit. Yeah.
And this gets to a point that Ad Bax has now been making for a while, that he thinks that a component of what masks are doing is independent of their controlling the dispersion from the source, and has to do with hydrating the airway and keeping us moist and changing the rheologic properties essentially of the airway. What do you think? What do you guys think about that?
Well, I think this goes a little bit outside my area of expertise. It's probably your area, Don, isn't it?
Well, I don't know. I think both of these are interesting ideas. If you've changed the hydration, you may have changed a lot of features about how the innate immune response will be able to trigger and respond, and also how well mucociliary clearance will work and how rapidly. One of the things I've been impressed with is that we see SARS-CoV-2 appear in saliva sometimes days before it appears in the nasal specimens. If it were landing in the nose first and mucociliary clearance was moving it down to the mouth, that's not what you would expect. But if it was landing in the intrathoracic airways and the mucociliary clearance was carrying it up to the mouth, that would make a lot more sense.
Mm-hmm. Yeah, I agree. Yeah, and that's very interesting and very difficult to really capture. So I know of studies where they looked at essentially removal of the tissue on animals, where to look at the role of humidity on the penetration through the mucus layer, and indeed like having high humidity is better for preventing the penetration deep to the target cells by the virus. On the other hand, then you also can create that aerosolization and therefore the trapping of that virus being in that mucus. And so then the question becomes, how are the properties of the mucus once they are removed in the droplet then interacting also to with the survival? I think there's a lot of very entangled and very interesting questions that are still not unknown.
And that may be quite dependent on what virus or
Exactly.
bacteria that you're talking about. In the case of influenza virus, we know that the hemagglutinin and neuraminidase are polarized on opposite ends of the filamentous virus, which is probably why in humans infections, it's filamentous and not spherical. And this creates what's called a Brownian ratchet that allows it to penetrate through the mucus. So one might expect, in fact, that a more liquid mucus might actually facilitate the Brownian ratchet and rapid movement, whereas drying it out might help. It's interesting to consider how does this really work? Mm-hmm. And in the case of coronavirus, it's spherical. How does it manage to get through the mucus layer? It's another interesting question.
I was going to also add the incredible variety, physiological variety between people. Something which made me realize some years ago when we did something opposite, inhalation studies, and our subjects were inhaling ultrafine particles from different combustion sources. And well, there was a big variation, but there was a curve. And then after analyzing the results, we saw that one person had 100% deposition. So not that usual deep 100%. And if not, that the person was complaining that they felt a bit uncomfortable during the measurement, we would have said, well, something happened during that measurement, but that made us think. And then we approached that person and say, well, we realized that you felt uncomfortable, but we really would like to confirm that whether this was real or not. And they agreed it was real, 100% deposition. And well, we didn't have funds to then to study deep characteristics of the physiology of that person, but otherwise all the breathing parameters, she had the same, well, within the norm, so 100% deposition.
And most of the deposition data has been modeled on spherical particles. Is there any view about MTB, which is a sausage-shaped organism that has an aerodynamic particle size of about 0.2 microns when it's in airflows, but when it's in the peripheral lung, where presumably flows are more, there's very little in the way of flows, it's more just dispersed. At that point, it would be 2 microns in size. Sorry about my dog. Do you think that is a mechanism that would enhance peripheral deposition of these organisms?
Well, I don't know. Equivalent when calculating any flow dynamic properties, equivalent diameter is recalculated. So if it had different shape or so it would be relatively easy to recalculate this aerodynamic diameter.
Is it a matter that as it gets to lower flow rates, that gravitational settling becomes a dominant factor, and the fact that it's a big long sausage causes it to fall out faster than if it were really a 2/10 of a micron particle?
Absolutely, yeah.
Which gets back around to another question. On the source side, it's been known now for probably 50 years that, maybe longer, that there's a phenomenon in which it's really entropy driven or hydrophobic interaction driven, where mycobacteria, but also other organisms that are less hydrophobic than most mycobacteria, segregate into thin films. And there's drainage of the liquid away from the film and the movement of the hydrophobic object, a virus or a bacteria, into that film. is the explanation for why we see high concentrations of these microorganisms in the air above seawater and in breath. And that it's early on, I saw a number of papers coming out where people were modeling atomization and basically saying, well, it's a bulk fluid atomization. Well, it's not. It's clearly not. And the dominant factor is this film burst phenomenon driving the aerosols.
Yeah, I completely agree with that. I mean, even for processes that are not even respiratory emissions, at the end of the day, the atomization even of bulk fluids turn out to be going typically through a film breakup itself, because you never have really a drop that then suddenly becomes two drops. You have always an aerodynamic forces or shearing that essentially creates a film that ultimately punctures, creates itself ligaments, and then these ligaments becomes droplets for most configurations. Sometimes it's directly film to micro droplets, sometimes it's film ligament micro droplets, but it's never bulk droplets transition. There's always a film ultimately involved. So absolutely, and the modeling of bulk, or just the bulk part, is really, even for physical processes and industrial applications, is the wrong model for atomization.
So Lydia Bourouiba, you've done this elegant modeling of these boluses and how this turbulent bolus is affecting both evaporation and transport in the environment. To what extent during speaking or even singing are these phenomenon dominant as opposed to convection in the room? I understand in cough and especially in sneeze, these are really strong driving factors. But in our studies where we observe somebody for half an hour while they're giving samples, we almost never see influenza cases sneeze. We very rarely have seen COVID cases sneeze. They do, COVID cases cough a little bit, but nothing like flu cases. And it really seems in COVID to be talking and singing that are driving it. So I'm really interested to know, what is the role of this gas bolus under those conditions?
Yeah, that's a great point. So that the figure I showed at the end is really, so you want to study these things in the extreme conditions. So that's what we started with, that with the coughs and sneeze. That's why we discovered the presence of even this cloud. But in fact, when we went back to look at, even just breathing, you have high enough Reynolds numbers, so essentially momentum, that the gas phase is still trapped, is still there. The model is the same, essentially mathematically. You don't have to revert back to considering isolated droplets, but it's just that the total energy of that is in that gas phase is reduced, which means that you still, to model the dispersal, have to account for that gas phase that is trapping these micro droplets from talking or breathing or singing. It's just that the original momentum would be lower than if you're doing coughing or sneezing.
But what is the distance that we would expect in an indoor environment with a very low, relatively low, but still moving air?
Yeah.
What is the distance we expect that cloud to travel?
So it would travel in still a consistent way, so essentially coherent still bolus, as you call it. I like that. Essentially, we're talking about 3 to 4 meters if you're talking about singing, depending. If it's very, extreme singing, so, opera type singing, generate essentially momentum that is similar to a cough, so that you're still talking about that distance of coherence. So up to, let's say, 4, even potentially 5 for very high, opera type singing. For talking, breathing, you're still within that 2 to 3 meter zone. But what is really the difference is that it's not just that the aerosols are just sticking there. You have these pockets of turbulent flow that might not be the full emission, but that can be detached and essentially still carry them in concentrated packet. And I think that that's really where, over those shorter distances, where the cloud stills remain important to incorporate, because if you were to just say, this is the total amount emitted and divided by the space around the person, ignoring these local concentration pockets, it would be a lower exposure. But including the concentration pockets, you can find these high exposure regions that are intermittent, but essentially potentially much more effective.
But when we go outdoors, we still see these plumes. Yes.
That's right.
And we had the chair of our virology department here contracted the infection very early in the pandemic and reported on his department website that he was convinced that he got it standing in line outside of a grocery store with a gentle breeze blowing down the line towards him. And he remembered, he said, standing there thinking, well, I hope nobody up front has it because I'm going to get it.
That's
And
right.
2 days later, the fever began.
Yeah, yeah.
So, and another virology professor here picked it up sitting next to somebody at a picnic table at an outdoor brunch. So outdoors is not an absolute, it doesn't instantly dilute because there's a large volume there to dilute the aerosol.
Absolutely. Yeah.
And I think the other question, if we can take another run over by a minute or two,
Yep, go for it.
is this really fascinating question about the TB negative, the suspected cases. Are they colonized? Are they truly infected? Do they develop a delayed type hypersensitivity response? And what does this mean for transmission?
Those are all questions which the work raises. So what was it in that group C? They certainly had viable organisms, well, metabolically active organisms. We haven't shown that they're infectious, but it would seem intuitively that would be reasonable. I think you mentioned the word colonized, and the reason that I think that might be the way forward is that latent infection it's a funny mixture that in order to have positive quantiferon or TSD tests, you do need continual exposure to antigens, and colonization would do that. In our part of the world, the majority of adults, 70% of them, have immunological evidence of previous exposure. And one of the other questions that came to mind was, at the end of 6 months treatment, would you prefer to be somebody who had totally cleared the infection, or someone who is now in immunological colonized balance with the infection? So I think it raises those sort of questions. So we need to follow those people prospectively. And then it also raises the question of what are vaccines trying to achieve? If you got people who are living in some form of immunological balance, is that going to be, what is your target of the vaccine? Is it to clear that? Is it to stop this sort of inflammatory progression to disease? So yeah, I mean, it's as with most scientific things, it's produced more ignorance and questions than it has solutions.
A very, really fascinating topic. And then, you know, enters into another whole topic about what are we trying to do with vaccines.
Yep.
Measles vaccine, I think, gave us a standard for what a vaccine can do that is almost in that and smallpox have given us a, you know, set the goalposts really far out and very high. And it's very hard to reach them with anything else. And one has to wonder I used to study the hygiene hypothesis of asthma and allergy pathogenesis. And one has to wonder, if we did eliminate all these infections, how bad would the allergy and asthma problem be? And so there is life is a dynamic balance. It's a homeostasis, and we have to try to understand where that balance is. But thank you for a wonderful discussion today and great presentations. I want to turn it back over to the conference organizers.
Excellent. I just want to echo one more time. Thank you so much, Don, for leading a great session today. And of course to Lydia, and Robin for some fantastic talks. I think the presentations and the discussion were really informative. Thank you very much to our audience for joining us today. As always, please take a moment to complete the survey that's linked in the chat box and give your feedback and give suggestions for future Life Science Across the Globe events. And don't forget to join us again on July 6th for Life Science Across the Globe, hosted by the University of Buenos Aires and CONICET in Argentina. And that one will be focused on gender policies in science.